Look at the second example of how to determine the empirical formula of a compound in the we do. So when we read through this compound contains carbon, it also contains hydrogen, and it contains oxygen. So we have to make sure that we do the math that includes all three elements. The other thing that you should notice is that instead of being given grams, liters, or a count, we're given a percentage. And we treat that percentage as the mass of the sample. The reason we can do that is if you add up these percentages, they add up to 100%. So 100% equates to having 100 grams of this compound. And so the carbon makes up 48.6% of all the atoms present, or 48.6% of the mass that is present. So here is our setup. So we're going to work with carbon. So we have 48.6 grams of carbon, and we need to change that mass into moles. And so mathematically, we want to end up with moles of carbon. We know that if we have 1 mole present, we have to figure out what we put next to the G in the equivalence. And so you need to remember that in our equivalence of moles to grams for a substance, we need to know the substance's GFM. And since this is an element, we can find that GFM on the periodic table. So 1 mole of carbon atoms will have a mass of 12.0 grams. And when you put this into the calculator, we end up having 4.05 moles of carbon. So now we're going to repeat the process for hydrogen. We have 8.1 grams of hydrogen. We need to convert that hydrogen's mass into moles. So 1 mole of hydrogen atoms, according to the periodic table, has a mass of 1.0 grams. And when we put 8.1 divided by 1, we end up with 8.1 moles of hydrogen. Now we'll carry the math on, but this time we will do it with the oxygen, and we have 43.2 grams of the oxygen. We need to change that mass also into moles. And 1 mole of oxygen atoms, according to the periodic table, has a mass of 16.0 grams. So 43.2 divided by 16 leaves us with 2.70 moles of oxygen. Next step. Once when we have each element present in the compounds, a quantity converted to moles, then we need to divide each of the mole values by moles. And we choose to divide each one by the lowest mole value. So 2.70 is the lowest of the 3 mole values. So we divide each of the elemental mole values by 2.70. Now notice, we are dividing mole by mole. So mole divided by mole, moles are gone in each of our setups. So once when you do the math and the last unit is completely eliminated, no more units, this is what we refer to as a ratio. And because the last unit eliminated is the mole, we'll refer to it as the mole ratio. So here we go. 2.70 divided by 2.70 means that there is now 1 oxygen present. 8.1 divided by 2.70, we have 3, and it belongs to the hydrogen. So far we have 1 oxygen present, 3 hydrogens present. Do the math for carbon. 4.05 divided by 2.70 indicates that we have 1.5 carbons present. And we use this mole ratio as the subscripts. So my empirical formula, based on the calculations, is carbon 1.5, hydrogen subscript of 3, and oxygen subscript of 1. But now we need to go back to the term empirical formula. So empirical formula, remember, is that lowest whole number ratio. Well, 1.5 is not a whole number. So when this happens and we have half of an atom present, that means to get to a whole number, we need to double the entire formula, not just carbon subscript, but all the subscripts to maintain the ratio. So 1.5 times 2 makes carbon's new subscript, that's a whole number, of 3. Hydrogen's subscript, 2 times 3 becomes 6. And oxygen's subscript of 1 times the 2, oxygen's final subscript is 2. So C3H6O2. The only thing that you can divide each of these subscripts together by is 1 to maintain a whole number ratio. So 3 to 6 to 2 is the lowest whole number ratio for this, based on this combination. So final answer, empirical formula for the we do is C3H6O2. You try the you-dos at the bottom of this page and the multiple choice questions. Check your answers with your teacher.